So the next person we're going to talk about, his name is de Broglie. And de Broglie is just amazing. But anyway, particles and waves, as we saw earlier, are usually quite different. But we saw that light can be both. It can be both. It can be the wave-particle duality, like we saw with Einstein's photoelectric effect. Well, de Broglie was amazing. He took two equations and he put them together, and he thought, there must be something to this. And it's a very simple thing that he did, but it's really cool. So anyway, what he did is he realized that E equals mc squared. And this is one of Einstein's equations. And it's more used in physics, and we'll use it in chemistry too. But the energy is related to the mass of an object times the speed of light squared. But then he also took Planck's equation, E equals h nu. He used the hc over lambda part. And he noticed that, hey, wait, both of these have an energy term. So what if I set them equal to each other? So mc squared equals hc over lambda. One of the c's cancels out, so you have mc equals h over lambda. If you rearrange that, you have lambda equals h over mc, but particles with mass don't travel at the speed of light. This is an Einstein thing. So he replaced it with a v velocity, and by the way, this is different than frequency v. This is a v like a speed, and he came up with what's called the de Broglie wave equation, which is this thing right here. Wavelength equals h over mv. And this equation is for particles with mass m traveling at a speed or velocity v. And at first you're like, okay, whatever. But believe it or not, this actually blew his thesis committee away. He was working on his PhD at the time, and they didn't know what to do with it. Because they thought, well, these are both good equations. Is this a possibility? So the rumor is they had to send his thesis to Einstein to say, hey, does this make any sense? And Einstein said, oh my gosh, give this guy his PhD right now. He's onto something really cool. De Broglie's thesis for his PhD was supposedly only about 7 pages long. Now, my PhD thesis was like 400 plus pages long. It was blood, sweat, and tears, man. But anyway, de Broglie's wave, his thesis was only 7 pages because I basically just put it up right here. And again, it's amazing. It's a true testament to innovation and science, and I think it's really cool. Now, why this is cool for what we're talking about is this shows the wave-particle duality for matter. Now, this is another thing that's really wild because you wouldn't think of a person having a wavelength. Like a person would move forward, or you throw a baseball and it would go forward. But we're going to see under certain conditions, particles can have a wavelength, which is pretty wild. So let's talk about that a little bit. Here's an example of how you can calculate the wavelength of a particle. Now, let's talk about an electron, a very small particle. The mass is 9.11 times 10 to the minus 31st. And particles can't travel at the speed of light, but they can get close to the speed of light. So let's pretend that this particle is traveling at 75% the speed of light. So you can calculate the wavelength. Well, Planck's constant, 6.626 times 10 to the minus 34. You divide it by the mass of the electron, and you have to use kilograms to make the units work out. Here's the speed of light, 2.998 times 10 to the 8th meters per second. But we're going to multiply the speed of the light by 0.75 because particles can't travel at the speed of light. Okay, well, anyway, you end up with a wavelength, 3.23 times 10 to the minus 12 meters. And believe it or not, this is a wavelength which is actually observable with the right equipment, which is totally crazy. Now, I want to make one warning about de Broglie. You have to use kilograms for mass in de Broglie's wave equation because a joule is really a kilogram meter squared per second squared, which isn't anything you have to know. But when you're using de Broglie's wave equation, just make sure you use kilograms. Literally every place else I can think of, chemists use grams for mass, like grams per mole, et cetera, et cetera. But with de Broglie, you have to use kilograms.
Electrons have wave properties. If we shoot a beam of electrons through thin metal foil, the atoms of the foil cause the waves to interfere with each other. The interference, or diffraction pattern, can be recorded on photographic film as a series of concentric circles.
An electron gun is kind of like a regular gun. Instead of bullets, though, it shoots electrons, all right? And if you shot a bullet at a piece of metal, it would make a hole through it, and that hole and that piece of paper on the other side would show a hole, all right? That's what you'd expect from a particle. But electrons can actually create wave patterns. So the pattern you see there in that video, it's like if you drop a petal in, or a rock in the middle of a clear lake or something like that, and the waves that go out would kind of be that way. And that's what people see with these electrons, which is just crazy. And nobody had considered this, but there's actually been lots of examples where you can literally see the wave behavior of electrons. Now, punchline, anything basically bigger than electron, you usually don't see the wave behavior. So you and me and baseball, stuff like that, no wave behavior.
Ooh, let me play this thing real quick.
Okay, well, because I'm male, or I'm sorry, because we're talking about wave particles properties of particles, I have to show this example of a baseball. All right, and this baseball in this video is being shot at 1,000 miles per hour at this target, and you can see it just devastates that target, that person they're showing there. But anyway, the important part is that you're not going to see any waves, and that's pretty fast, 1,000 miles per hour, but it's not near the speed of light. It doesn't have the same mass and stuff like that. So punchline is that de Broglie wave equation is great for really small particles traveling close to the speed of light, but it doesn't work you won't measure anything for baseballs, you won't measure it for you and me walking down the street, stuff like that. It's only for very special cases. But we're seeing on this quantum world, this really small area of atoms and stuff like that, things get weird. Electrons start behaving as particles and waves. Light starts behaving as waves and particles. Whoa. Another player in all of this was a person named Heisenberg. Heisenberg was another scientist who was working on all this stuff at the same time. And Heisenberg came up with a thing which we'll use here later on called the uncertainty principle. And he realized, for ways that we're not going to talk about in this class, that there becomes a point where you cannot simultaneously define the position and momentum of an electron at the same time. Like, you have to make a choice. Now, momentum in physics, you'll see, is related to energy. And what this is going to mean here in a little bit is that we won't be able to know the position and the energy of an electron at the same time. We're going to have to make a choice, all right? And so what people basically do in chemistry is the energy is key. All the physical sciences like chemistry are after the energy. So we're going to know the energy to high precision. We're going to know it pretty well, but at the very best for position, we'll have like a kind of an overall area it's going to hang out in, but it's not necessarily there. So as an example of this, like, I lecture in a big lecture room on Mount Hood Community College most of the time, and almost all the time you can figure out my energy. Like, if you watch me lecture, you'll know if I'm high energy, have like caffeine, whatever, or some days I come in kind of low energy. You'll be able to tell that right away. But you may not know exactly where I'm going to be. Like, most of the time I'm right next to my computer and the instructor's podium in that room, but sometimes I vary. Like, sometimes I'll go way over on the far left or the far right or up the stairs and stuff like that. So in terms of me lecturing, you'll know my energy very well, but you'll know most of the time I'm kind of by my computer and the podium, but sometimes I go all over. That's the idea with electrons. We're going to know their energy like super well, but we'll only be able to guesstimate where they are. We'll have their most probable locations, but we won't know exactly where it is. And that's another fascinating part of this quantum world.